Right. So we are going to look at stress and strain. Uh, all right. So essentially, we get three types of stresses. Right. So you have direct stress, right, which is the one we are going to look at first. You get direct stress, you get shear stress, right, and then you get bending stress. So if you come across a question where they ask you to name at least two or three types of stresses, right, the correct answers are direct stress, shear stress, as well as bending stress. So you have direct stress, right? Second one is shear stress, and then you get bending stress, right? You will not be getting marks if you say tensile stress, compressive stress, because tensile stress and compressive stress, for instance, both fall under direct stress, right? So essentially, types of stresses include direct stress, shear stress, as well as bending stress, right? Now, under direct stress, we get tensile stress as well as compressive stress, right? We get tensile stresses as well as compressive stresses, right? Like I said, both of these, right, fall under direct stress, right? And this is the symbol we're going to use for direct stress, right? The symbol doesn't matter much though, right? What matters is how you would have to calculate any quantities that fall under direct stress. So those quantities are, now this is how we express stress mathematically, right? We say direct stress is equal to the force that the material is being subjected by, divided by the cross-sectional area of that material that you're looking at, right? So this is the general formula for direct stress. And then, of course, it depends if the force is a tensile force or if the force is a compressive force, right? Are we still together here?
Yeah.
Right. So this is the general formula for stress, right? It is synonymous with the formula we use for pressure. Remember, pressure is also equal to force over area, right? Right. So if you have direct stress, you get direct strain, right? Now, direct strain is what is caused if you apply or if you subject a material to a stress or a force, right? You get, so if you subject a material to direct stress, right, this is what is going to be induced, direct strain, right? Now, direct strain, this is the symbol we use for direct strain, right? And then to calculate direct strain, we use change in x over L. Now, change in x refers to the deformation or the change in length that is caused due to deformation, right? If you apply or if you subject a material to some stress, right, it is going to be subjected to some strain or some change in length, right? Now, the change in length might not be visible to the naked eye, right? But you always get some change in length if you subject a material to some direct stress, right? And that deformation or that change in length due to a deformation, we refer to it as change in x, right? And then L stands for the original length of the material you are looking at, right? Now, stress, its unit of measurement is Pascal, just like pressure, right? So stress is in is measured in pascals, right? And as we know, a force is measured in newtons. Cross-sectional area is measured in square meters, right? The change in x will be in meters. The original length will also be in meters. So that is to say that your direct strain is dimensionless, right? It has no units, right? And then you get shear stress, right? This
Sorry,
is the
sir, say that again. What has no units?
direct strain, right? So if
Direct
if
strain.
change in x if change in x is in meters and the length is in meters, it means the units are going to cancel each other out,
Yeah.
Hence, this will be dimensionless.
Cool. Thank you.
All right. And then you get shear stress. Right. This is the symbol we use for shear stress. Right. The general formula, just like direct stress, is force over area, but for shear stress, right, we make use of the shearing force, right, and the area will be the area of cut. All right. So the area we use is the area that will be essentially either if the material is being cut, right, the area of cut will be the area that has been cut, right, as opposed to cross-sectional area, right. Now, it could happen that the area of cut is equal to the cross-sectional area and to end up using the cross-sectional area, but it is important to note that for the area regarding the shear stress or the area we use here, right, this would be the area of cut, right, depending on how the material would be cut or how the material is being cut, right, or how the material is being subjected to a shear stress, right, in which portion of the material is the material being subjected to shear stress, right. So that is the area you use. We refer to it as the area of cut, right? So if you have shear stress, you get shear strain, right? And then for shear strain, this is the symbol we use for shear strain, right? As far as how we express the shear strain mathematically, right, it is the same as direct strain. It's changing x over the original length, right? And then you get bending stress. Now, bending stress, this is how you calculate it. But in N4, we don't necessarily look at bending stress, right? We just take note of the fact that we have a type of stress that is known as bending stress. Otherwise, bending stresses you will look at in N5 um, when you guys are doing what is this strength of materials, right? So we don't necessarily dwell much on bending stresses, in fact, at all, right? Right now, I will be sending you this document, but I did mention here that bending stresses is beyond the scope of engineering science N4, right? And that you can expect to look at bending stresses when you guys do strength of materials in N5 and in N6. Right? Any questions so far?
No, sir.
Right. Right. Now, let us get into some of the properties um, that are important for stress and strain at this level, as in engineering science N4. Right. By doing so, we have to do so in conjunction with this stress strain graph. Right. Now, if you look at this stress strain graph, right, on the y-axis you have stress, on the x-axis you have strain. Right. Now, in N4 we only deal with the part of the graph where Hooke's law is satisfied. Right. That is why I'm saying at this level, right, as much as we are going to look at some of the mechanical properties that you can expect to be asked about, right, properties um, that essentially our calculations will essentially be based on, right, those mechanical properties, right, those mechanical properties begin from, if you look at it from the perspective of the stress strain graph, begin from zero to essentially, or let me say, we only base or we only look at the mechanical properties that are involved in the elastic region of this stress strain graph, right? Hence, me saying we only look at the mechanical properties where Hooke's law is being satisfied. Now, Hooke's law is only satisfied essentially in the elastic region, right? Beyond the elastic region, Hooke's law is no longer satisfied, right? I will get into how we define Hooke's law, right? So that this makes more sense, right? But as I'm saying, Hooke's law is only satisfied in the elastic region. Beyond the elastic region, Hooke's law is no longer satisfied, right? So for stress and strain at this level, we only look at the mechanical properties that are involved where Hooke's law is satisfied, right? And Hooke's law is only satisfied in the elastic region, right? Now, one of the mechanical properties we tend to look at is elasticity, right? Why? Because elasticity is the mechanical property that is satisfied only in the elastic region where Hooke's law is being satisfied. All right. Now, what is elasticity? All right. Elasticity, I've defined it here. It refers to the tendency of a material to return to its original form when a force causing the stress that causes the strain is removed. All right. So that is to say that if you subject a material to some stress, right, it is going to undergo some form of deformation. Now, the deformation might not be visible to the naked eye, right? Sometimes the deformation is such that it is only internal, depending on how much stress the material is being subjected to, right? And then sometimes, based again on the stress that the material is being subjected to, right, you actually get to see the deformation, right? The deformation would be in the form of the material, say, bending, right? Now, if you subject a material to some stress and essentially it bends, if you remove the stress that is causing that deformation and the material is able to go back to its original form, right, that mechanical property is known as elasticity. Right? So as long as if you remove the stress that the material is being subjected to and the material is able to go back to its original form, it means the material is still elastic, right? Meaning that it is still in this elastic region, right? Now, I also said, yeah, material is able to return to its original form as long as its elastic limit is not exceeded, right? So that is what I've just explained, right? If you look at the graph, right, there's a lot of points on the graph, right? So the graph, this is the graph here, right? Now, like I said, we only focus at this level on the part of the graph where Hooke's law is being satisfied. So that is P, E, and Y, right? Now, this point P is referred to as the proportional limit, right? And then the point E is the elastic limit, right? So that is to say, at the elastic limit, that is the point where the material is still elastic, right? So meaning that beyond this point, right, beyond point E, the material begins to yield, right, to the stress that the material is being subjected to, right? And then of course beyond the yield point, right, the material essentially succumbs to the stress that is being subjected to it is being subjected to, right, and it completely deforms, right, and meaning that after or beyond this point the material is no longer, even if you remove the force or the stress that the material is being subjected to, even if you remove it, it won't be able to go back to its original form, right? That is beyond the yield point, right? The elastic limit refers to the maximum stress that a material can take and still return to its original form, right? That is just what I've just explained, right? I will be sending you these documents so that you are able to go through it, right? Any questions regarding elasticity, right? Regarding the elastic region, regarding the 3 points that you get under the elastic region? No question. Right. So let us get into Hooke's law. Right. Now, Hooke's law states that for an elastic object, the stress is directly proportional to the strain it is causing. Right. If you look at Hooke's law from the perspective of the graph, right? So in the elastic region, right? The graph here is a straight line, right? The graph is a straight line, and in this part of the graph, seeing that the graph is a straight line, it means that the stress is directly proportional to the strain, meaning that as the stress increases, the strain increases as well, right? So in this part of the graph, right, so the part of the graph where the material is still elastic, that is the part of the graph where the stress or the direct stress is directly proportional to the strain that is being caused. Right, so that is what essentially Hooke's law is. Right, right. So that is what Hooke's law is. Right, Hooke's law is only satisfied in the part of the graph that is a straight line. Right, because it's only in that part of the graph where where the stress is directly proportional to the strain. Right, if you look at the graph, right, it's only in this part where if the stress increases, right, the strain increases as well, right? But if you look at beyond this graph, right, if you look at beyond the elastic region, right, the the graph is no longer a straight line, right? There's a bit of a dip here, right, meaning that as this increases, right, as in beyond the elastic region, right, the stress is no longer directly proportional to the strain, right? Something else completely happens, right? So if you forget how to define Hooke's law, right, you can always look at it from the perspective of the stress strain graph, right? Bearing in mind that Hooke's law is only satisfied in the elastic region part of the graph, right? And then also we are also able to express Hooke's law mathematically, right? If Hooke's law states that essentially stress is directly proportional to strain, but only in the part of the graph where the graph is still, or where the material is still elastic, right? Putting that mathematically or expressing that mathematically, this is how you'd express it, right? That what is important here is that this is only satisfied when the object is still elastic, right? So when the object is no longer elastic, right, Hooke's law is no longer satisfied. Right. So as far as how to express Hooke's law, the most important part, as much as the stress is directly proportional to the strain, right, the most important part is that if the material is still elastic, right. Hence, when having to state Hooke's law, you also have to state that the stress is directly proportional to the strain as long as the material is still elastic, or if the material is still within the elastic region, right? So mathematically, this is how you express it. Stress is directly proportional to strain. This symbol is known as a proportionality sign, right? This is a proportionality symbol, right? Hence, we're able to say that stress is directly proportional to the strain, right? Bearing in mind, of course, that that is only possible when the material is still in its elastic region, or if the material is still elastic, right? Now, to get a formula that we can use mathematically, we essentially have to replace the proportionality symbol with an equals to sign. And in order to be able to do that, we have to introduce a constant, right? So meaning that in getting rid of the proportionality sign and replacing it with an equals to sign, we have to introduce a constant, and that constant is this E, right? This constant stands for Young's modulus of resiliency, of Young's modulus of what is this thing? Young's modulus of elasticity, right? Because you get, depending on the kind of stress that you're looking at, right? For direct stress, you get Young's modulus, or the way we denote the symbol for Young's modulus of resiliency for direct stress is, we call it Young's modulus of elasticity, right? For shearing stresses, we call it Young's modulus of rigidity, right? But at this level, we don't necessarily, let me see, yeah, we don't necessarily look at Young's modulus of rigidity, right? only Young's modulus of elasticity. Right. So again, this E stands for a mechanical property of a material that we know as Young's modulus of elasticity. Right. Any questions there? No questions. Right. So this is the part that I've just explained. Right. So let us look at Young's modulus of elasticity. Right. So in having to define Young's modulus of elasticity, you can simply say that it is the mechanical property of a material that resists deformation. Right. So as long as the material is able to resist deformation, right, that is the part of the material where Hooke's law is being satisfied. Right. Now, from this formula, right, stress is equal to E times epsilon. Epsilon is the direct strain, right? This symbol is known as epsilon, right? So don't be confused there. When I refer to epsilon, I'm referring to this symbol, right? So from that formula, right, if you solve or if you make the Young's modulus of elasticity, so E, if you make E the subject of the formula, right, E will be equal to stress divided by strain, right? So that is where this comes from, right? So E is equal to the direct stress divided by the direct strain. That formula we get from Hooke's law, right? This formula is essentially Hooke's law, or we get from Hooke's law, right? Now, direct stress, as discussed earlier, is equal to force over area, right? We know that this year direct stress is equal to force over area, and that strain, direct strain, is equal to change in x divided by the L. Right, that is where this comes from. Right, so this is direct stress divided by direct strain, which is change in x over change in L. Right, and then we know mathematically we need to change this to a multiplication sign, and if we do so, right, if we change the division sign to multiplication sign, right, we need to use the inverse of this. By inverse, I mean the denominator becomes the numerator and the numerator becomes the denominator. That is how this comes about, right? So essentially, this means Young's modulus of elasticity is equal to force times length, original length of the material, divided by the area of the material times change in x. So depending on what information you've been given, right, you can either use this over this, so meaning that if you've been given the direct stress and you've been given the direct strain, or you happen to first calculate the direct stress and direct strain, then to get Young's modulus of elasticity, you can simply use this formula, right? Otherwise, if you instead have a force, you have the original length, you have the change in length, right, and then you have the original area, you can simply use this formula to get Young's modulus of elasticity. Are we clear?
Think so.
Yeah.
Right. So those are the only mechanical properties we look at as far as stress and strain and Young's modulus of elasticity. Any questions?
So I think I don't understand the graph part.
What did you understand here?
I heard you say Hooke's law is satisfied, so it's satisfied where under that region of elasticity.
Okay, let's look at
So
Hooke's law. Let's look at Hooke's law. Right. What does Hooke's law state? It states that for an elastic object, so only when the object is elastic, the stress is directly proportional to the strain it is causing. Now, if we go back to the graph, this here is the elastic region, right?
yes, sir.
So, meaning if this is the elastic region, remember Hooke's law, as much as it says that stress is directly proportional to strain, right? It also states that only if the material is still elastic, right? And the
Okay.
material is
Yes.
only elastic in this part of the graph.
Okay.
Do you
Yes,
hear that?
yes, I do.
When two quantities are directly proportional to each other, it simply means that as the one increases, the other one increases as well, and vice versa, right? As in, if the one decreases, the other one decreases as well, right? And that is only satisfied in this part of the graph, right? If you look at the graph here, right, if you were to calculate, say, the Young's modulus of elasticity, right, at that point, right? So from here, right, from zero to there, and then from zero to here as well, you see that the strain is increasing. So as so if you were to again look at it, say there, let's call this one, call it two, call it two, right? If you look at just the parts that I've marked here, right, if the stress increases, the strain increases as well, right? Again, the stress increases, the strain increases as well. That means that the stress in this part of the graph is directly proportional to the strain. Why? As the stress increases, the strain increases as well. Do you see that?
Yes, I do. Sir.
Right. So that only is satisfied in the straight part of the graph. Right. Once the graph starts getting curvy, right, Hooke's law is no longer satisfied. Right. Why? Because the stress is no longer directly proportional to the strain it is causing. And then also that is caused why? Because the material is no longer elastic, right? It is completely deformed, right? Beyond this point,
Okay.
it means the material is completely deformed.
It
Kabish?
cannot go back to its original shape.
Sorry,
Cannot go back to its original shape.
I didn't hear that part.
Once it has passed the heal point, it cannot go back to its original shape.
Exactly.
Like,
Yes.
yeah.
So that is to say, even if beyond this point, even if you remove the stress that the material is being subjected to, right, it no longer goes back to its original form, right? It remains completely deformed. Are we clear?
Yes, capiche. So,
All right. Any more questions before we move on? No questions. All right. Let us look at a couple of examples. Excuse me. Mm, can everyone see here? Can you guys see the problem I've just attached?
yes, yes, sir.
All right. Let us look at this problem, right, and how you attempt such a problem. All right. Remember to
Yes, sir.
mute your mics until maybe you need to say something or you need to ask something.
Can I ask you something?
Uh, yeah. Thank
Sir,
you.
can I ask you something?
Yeah.
Um, Young's modules measured in Pascal also.
Yes.
Okay, because I've
It's
seen
measured
that
in,
it's gamma Pascal,
it's gigapascals.
gigapascal. Okay,
Gigapascals, yes. So
okay.
you get pascals. Um,
So that means we're
you
gonna
get
multiply by 10:9.
yes, exactly. So
Okay,
you get kilopascals, which is which is times 10 to the 3. You get megapascals,
okay,
which is times 10 to the 6, and then you get gigapascals, which is times 10 to the 9.
all right.
Right. Right. So 6.1 state Hooke's law. Um, I'm not expecting that you know how to state Hooke's law at this point, but I will be sending you that handout, right? What we just looked at, right? But again, Hooke's law, the main point is that you understand that Hooke's law is only satisfied in the straight parts of the stress strain graph, and the straight part of the stress strain graph represents the elastic region, right? So even if you forget how to define it, just look at it from the perspective of the stress strain graph, right? The fact that Hooke's law is only satisfied in the elastic region, right? So you look at the fact that in the elastic region, the stress is directly proportional to the strain, and that is what Hooke's law is essentially, right? Hooke's law, right, states that as long as for an elastic object or for an elastic material, the stress is directly proportional to the strain, right? However, however you choose to put that in words, right? As long as you do mention that the stress is directly proportional to the strain, as long as the material is elastic or is in the elastic region. Are we clear?
Yes, capiche,
Right.
sir.
So let's look at 6.2. The figure below shows a mild steel bar which is actually loaded by means of a tensor load so that the maximum induced stress is 120 megapascals. Young's modulus is 200 gigapascals. Right. Question is calculate the total change in length. Right. Now, as far as change in length, right, they're referring to the change in x. Right. This is what they are looking for. Are we together here? Hello.
Yes,
Yes.
All right. So they're looking for the total change in length. Now, if we look at our material, or if you look at our object, it is a composite object, right? It is a composite object. Why? Because it has three excuse me, it has three different areas essentially, hence making it a composite material, right? So meaning that you have to find the change in length here, change in length here, and change in length there. And once you have that change in length, you can simply add it to get the total change in length, right? Now, what have we been given? We are given the stress, right? We've been given the stress. The stress here is 120 megapascals. We have Young's modulus of elasticity, which is 200 gigapascals, right? Now, we are looking for the change in x, right? And in order to get change in x, we know that change in x is in that formula for direct strain. Direct strain is change in x divided by the original length, right? And you have the original length of the of the parts of the composite object, right? So this part of the composite object is 200 millimeters. This one is 175. This one is 150. in order to be able to say get the to get the to get the change in x, right, you first need to be able to get the force, because the force being applied is just one force, right? You only have one force being applied, which is this one. This is essentially attached to some wall, right? But it is attached to something here, right? And then this tensile force is being applied, right? So you have one tensile force being applied. So in order to be able to calculate the change in x, you first need to calculate this force here, because this force is the force that is applied on this same force that is applied on this part of the composite object, also the same force that is being applied on this part of the composite material, right? Remember that E is equal to, it is equal to direct stress divided by direct strain, right? And then direct stress is force over the area, right? And direct strain is changing x over changing L, but changing, right, changing this division sign to a multiplication sign, we get the inverse of this here, meaning that here you will have L over changing x, right? So essentially meaning that we can use E is equal to F times L divided by cross-sectional area times the change in length, right? Now, if you look here, this is what we are looking for each section of the composite material, right? We're looking for change in x. We have the length of each section. We've been given the diameters of each of the sections. So essentially we have the area of each section. We have the Young's modulus of elasticity for the material. So it means we have, as things stand, we have two unknowns, but we can get this unknown because we have enough information to be able to calculate the F. Right, so question is, how are we going to calculate F?
Sir, can I ask you something?
Uh-huh.
Are you gonna be so in this case, because this formula we have this formula just put down there. We have it on the formulas on the question papers.
Sorry?
So my question, I'm saying this formula that you wrote there, we have it on the question paper also.
Okay.
Yeah. So my question is, you say we have two unknowns. So because the area they differ, are we gonna have to calculate each and every area in each section?
We're going to?
Are you going to calculate area in each section?
Are
Because
we
the
going to
force is the
calculate?
same.
Are we going to calculate
Area,
the area in?
area for each section
Are we going to calculate the area in
separately.
section?
Yeah, because in the first section we have 50 diameter, in the second section we have 40, then 30.
Yeah.
That's my question.
Oh, I see your question. Right. So
Yeah.
we are only going to calculate using one. We are going to calculate the force using one section. Using one section,
Okay. I don't
and that
understand.
section
What about the area?
and that section. Now remember, the force that is being applied here is only one force, right?
Yes, sir.
It's only one force, right? And that force is essentially being applied. Is essentially being applied at this point, right? At this point of the composite material. So because the force is being applied at this part of the composite material, we are going to calculate the force using the first area.
Okay.
Right? We calculate the force
Okay.
using the first area.
Okay, sir.
Right? Because essentially that is the only force being applied here. Right? And then we also have to take into account that since this So this means that this side of this composite material is attached to something. All right. So meaning that as you pull from this side, if this remains static, it means that the same kind of force is being pulled in the opposite direction. Right. But the point here is that the force, or how you are going to calculate the force, right? You simply use the first area or the first section of the composite material.
Okay.
Right.
Okay, sir. All right.
So meaning that once you have that force, right, you will have eliminated one of the unknowns, and then you can
Okay.
make this one the subject of the formula and calculate the change or the changes in length for each section, and then you simply add the changes in length.
All right. All right. I got you.
All right. So the first thing is to get the force. Right. Direct strain is equal to force over area. So this will be force. Now each of the sections, right, the section we are going to use is this one, and in fact all the sections we've been given the excuse me, the diameter of each section, which means that each of the sections are circular in shape. Hence the cross-sectional area will be 1 for a circle. So meaning that the area will be pi over 4 times the diameter. Right. So bearing that in mind, it means here you are going to have times 4 divided by pi times d squared, 4 squared, d squared. Right. And then from here, we solve for f. So we make f the subject. Right. Making f the subject. Right. Making f the subject, it means you will have direct strain times pi times d squared divided by divided by divided by 4. Right. So here you get direct stress, which is 120. So that's 120. Remember, that's megapascals. And how you substitute the direct stress must be in pascals. Right? So you have to convert the mega to pascals. Right? Like I said, mega is times 10 to the 6. Right? So 1 megapascal is equal to 1 times 10 to the 6 pascals. Right? Times pi times d squared, 30 millimeters is equal to 0.03 squared divided by 4. And what do you get here?
27,000.
What do you got?
27,000 newtons.
This is 27,000 newtons. All right. Are we all getting the same thing here? Hello? Are we all getting the same thing?
Yes, sir.
Okay, so this is 120 times 10 to the 6 times pi over 4.
Sir,
Yes?
I got 84,823. That 27,000 you still have pi on it.
So fire.
Sorry?
The answer
I
is
think
sorry. Mm, sorry.
84,823.
Okay, let me calculate it as well. 120 times 10 to the 6 times pi over 4 times 0.0203 squared. Oh, it's 27,000 pi, which
With
if
pi, yes.
okay, I see. So this is actually, so you're supposed to change that to decimal form. So this is what you get, 84,823. So you can either write all of that, or you can simply press engineering notation there, and you get 84,823 kilonewtons. Do you understand what I did here? You guys understand by what I mean by engineering notation, right?
How's that
Yes,
physics
sir,
lab?
we do.
Oh yeah, I know. Sorry.
Got it, no?
Yeah.
All right. Right. Once you have the force, so we have the force being applied, right? Now we'll be able to get the changes in length, right, in each part or in each section of the composite material, right? And that you do by solving for x in this formula, right? So making x the subject of this formula, right? So you have change in x is equal to, so if you make this x the subject here, you will have force times length divided by E times the area, right? Bearing in mind that the area, remember, is equal to pi over 4 times d squared, right? So that means this will be force times length times 4 divided by E times pi d squared. Are we in agreement here? Yes. Yeah.
Yeah.
Yeah. That is how you would manipulate the formula. All right. So now you calculate the changes in length for each section essentially using this formula. All right. So the first section is the 30 diameter millimeter diameter section. Second one is 40. Right. Third one is 50. Right. So we now calculate the changes in length for each of the section using this formula. Right. Simply say change in x for say the 30 millimeter diameter part of the composite material. Right. We already know that this is the formula for it. All right. So all you do is simply substitute. So F is 84,823 times 10 to the 3 newtons. The original length of the 30 millimeter diameter section is 150 millimeters. Remember that you convert to meters times the 4.
So,
Yes?
sorry, are we sure that that area formula inclusive is correct? 4 over pi d squared.
4 over pi d squared.
Yeah, is that correct?
You mean the formula for the area of a circle this year?
That's as it pi over 4d squared. Or am I
Yes.
just reading it wrong?
It's pi over 4 times d squared. This is
Pi
the one.
over 4. Okay. So
So
pi over 4 times.
it would be pi times d squared over 4, essentially.
Pi times d squared over 4.
Yeah.
Okay, got you. I'm writing it wrong here.
Okay.
Thank you.
Cool. Right. So E is, what is E equal to? 200 gigapascals. Remember this, you have to substitute as pascals. Giga is times 10 to the 9 pascals. Right. Times pi. The diameter is 30 millimeters. That's 0,03 squared. All right. And you should get the change in x here. What is this equal to? Now, the changes in length practically speaking, are always like very small. Hence, if you remember, I said for the most part, if a material, be it composites or just solid, or just one material, right, or just one object, um, you find that you cannot see the changes in length with the naked eye. Why? Because the changes are so small that sometimes you cannot tell with the naked eye that the material has changed in length. All right, so you're gonna find that for the most part, the changes in length are very, very small. Right, you're gonna get like really small numbers. Hence, for the most part, you would have to make use of engineering notation. What do you get here? Maybe let me calculate this as well, so you can see what I mean.
It's 9 times 10 to the power minus 5.
Right. See, that is very small. So 84, comma 823 times 10 to the 3 times 0.15 times 4 divided by 200 times 10 to the 9 times pi times 0.03 squared. Right. So the number you get, so I'm getting here 8,957 times 10 to the negative 5. Are we getting the same thing? All right. This is the number I'm getting.
Yes, sir.
Right. Now, with small numbers, because for you to get a perspective of how small this number is, on your calculators, press shift and general notation. Right. So do that until that times 10 to the exponent on the right hand side is 0. Right. You should get 0, 1, 2, 3, 4, 0, 0, 0, 8, 9, 5, 7, 5 times 10 to a negative 2 to the 0. So until you see something like this, right? The point here is that this number is that small. So that is what I meant by the changes in length, right, being so small that you cannot see them, or you cannot see the change with the naked eye. Are we together?
Yes,
Yes,
sir.
sir.
Sir, will it affect your answer if you don't press engineering notation?
Um,
If you have,
it,
will you
it,
be wrong?
it will affect your answer. Why? So, for instance, if you are if under the instructions you are told to leave your answer to round off to 3 decimal places, right?
Yes.
So essentially your answer will be 0,000. Do you see what I'm saying?
Yes, sir.
Right. So it is better for accuracy purposes to use engineering notation, right? So for instance, here you would have 89,576 times 10 to the negative 6. And remember that this is in meters.
Mm-hmm.
All right. So for accuracy purposes, that is why we use engineering notation.
Okay. All right.
All right. So now we do the same thing for the 2 other sections. Excuse me. So you have the change in x for the 40 millimeter section, right? Yes. The length for that section is 175. So you have 84. Remember, the force remains the same. 823 times 10 to the 3 times the length, which is 175. So 0,175 times 4 times 4. All of this divided by 200 times 10 to the 9 times pi times the diameter, which is 40 millimeters, so this is 0.04. And what do you get here? Remember to use engineering notation.
0.04 squared, sir.
Press engineering notation there.
I'm saying at the bottom here where you have 5 times 0.04, isn't it times 0.04 squared?
Oh, yes. Squared, yes. 100%. Thanks. What are we getting? 0.4. So the only change is really the length and the diameter. As in, you don't necessarily have to punch the whole thing again. You can just go back to this one and change the length and the diameter. It will be much quicker like that. So I am getting here 58,784 times 10 to the negative 6 meters. Are we getting the same thing? Hello?
What are you getting? 58, sir.
I'm getting 58.
I'm getting 59. Just check my answer.
I'm also getting 59.
So all of you are getting 59.
Yeah. 59,02062.
Okay, that's fine. That's more or less the same thing.
So
Right.
on my calculator, I'm getting 5,906.
Yeah, so press engineer notation and you should get 59 like everyone else.
Yeah.
Right.
There is she's getting 5,906 times 10 to the power negative 5.
So press
Yeah.
engineer notation again there until it's negative, until it's times 10 to a negative 6. So you are getting 59, comma.
Yeah. It's 59 times. When I press engineering notation, it's 59,062 times 10 to the power
0.62 times 10 to a negative 6 square meters, not square meters, meters. Right. And then you calculate the last one, 50 millimeters. Right. So essentially the same formula. With changes in the length and the diameter. The diameter is now 50, so 0.5. Excuse me. The length is 200. So this is 0.2. Right, and see what you get. So that's now 0.2 which is 0.05. And what are you getting here? What is this equal to?
Hmm. 43,2 times 10 to the power minus 6.
43,
2 times 10 to the power minus 6.
times 10 to the negative 6 meters. Right? And then to get the total change in length. Right, so remember the question
Sir?
here. Yes?
Sorry, let me take you back again. Even when I get 4,319 times 10 to the power minus 5, it will still affect my answer.
Yes. Hence, I'm saying this is simply for accuracy purposes. Right? Now, this is how things are going to be done in strength of materials, right? You are always going to have to use engineering notation, right?
So I must
So
always use I must always write my answer when it says times 10 to the power -6.
yeah,
Or it's
it's
not
always
always the
better to
case.
leave it as times 10 to a -6. This is for accuracy purposes. By accuracy purposes, I mean if now you have to make use of this value, right? Your answer
Yes.
will be more accurate, right? If there's more numbers than zeros, right, in your value. So
Okay.
the engineering notation helps in increasing the numbers in the value, or let's say to decrease the number of zeros in the value.
Okay.
Yeah?
Okay, sir.
Right. So remember the question was to calculate the total change in length, right? Not the final length, but the total change in length. All right, so because they just want us to calculate the total change in length, so now you can say the total change in length is equal to change in x for the first section plus the change in x for the second section plus the change in x for the third section. All right, so this is equal to, now if you look at your answers, right, all of them are in terms of times 10 to the 6. Do you see that?
Yes, sir.
Right, so all of them have this common factor. Right, all of them have this common factor. So all you can do here is simply add, like for instance, in your calculators, you're just going to punch 89,576, exclude this, just say 89,576 plus 59,062 plus 43,2. Right, so 89,576 plus 59,062 plus 43,2. So here I am getting 191,838. And then here you can include the times 10 to a -6 meters.
Is that now the final answer, sir?
Yes.
Calculate the total change in length. Okay.
Again, the same thing.
Is this now? Yeah.
Yes,
Is this,
sir.
is this a typical question you will get in the exams? Like the normals.
Sorry?
Is this now one of the typical questions you will get in the exam, sir?
Yes, this is an exam question. I just don't remember which one,
Which
but
one?
yeah. But yeah, this is an exam question.
I think it's 2022.
Right. Past papers are on Module. So you can use those. And then if you have any questions, you can of course either message me personally or send them in the group or email me.
Sir, on the first area that we use there on top, do we the one that we use to get the force, do we use that one, or even if we choose either of the area there, we're still gonna get the same answer, or is strictly the last one?
Second,
The area that we use to get the force, do we use only the first one, or we can use either of the area on
yeah,
there?
always use the first one.
Okay. So there is no way that they're gonna give us the information, but we don't get the diameter of the last one.
Of the last one. You could if you've been given this force.
Okay.
Yeah. You can't have two. They can't give you a problem where you have too many unknowns. So if one of the diameters, if you have to calculate, say, one of the diameters, they'd have to give you this force.
Okay, sir.
All right. Excuse me. All right. Let us look at another problem. Uh, mm, okay, so this one is pretty straightforward. During a tensile test on a round bar of 25 millimeter diameter, a load of 80 kilonewtons causes an extension of 0.2 millimeters. If the initial length was this, calculate the following stress, strain, Young's modulus. Okay, so this one is pretty straightforward. I don't think we should do this one because it's pretty straightforward. You are given,
Straightforward, sir.
yeah, this
Sorry,
one is
sir.
pretty
Sorry.
straightforward. You are given the change in
Um,
x, you are given the diameter, you are given the force, you are also given the original length. You are asked to calculate the stress. We know stress is force over area. You have the force, you have the diameter, so you can get the area, so you can get the stress. Strain. Strain is change in x over the original length. You've been given, right? You've been given the extension, that's a change in x. You also have the original length, so you can get the strain. Pretty straightforward. And then to get Young's modulus is stress over strain, which you will have calculated. So we can skip this one, right?
Yeah.
So this one is pretty straightforward.
sir,
Uh-huh.
can you do that one of a hook, because there's I've seen that the force is distributed equally in both sides. What? I don't know if you know what I'm talking about.
I think so. I think I know what you're referring to. Okay, so let us do this one. Right, figure 3 shows a clevi type hook. Clevi will be attached to a rope that needs to lift up a load of 15 tons. The maximum shear stress in the pin of 45 millimeter or 45 megapascals should not be exceeded. Right. Okay, let's see what you've been given. You have the mass that needs to be lifted. It is 15 tons. 15 tons is the same as 15,000 kilograms. Right. The standard unit of measurement for a mass is kilograms. So if you've been given the mass in tons, you always have to convert to kilograms. And 1 ton is equal to 1,000 kilograms. Right. The maximum shear stress in the pin. So we have the maximum shear stress, which is 45 megapascals, should not be exceeded. Right. So that is what we are given. Calculate the diameter of the pin suitable for the task. Right. Now, obviously, the what is this? The so you have a rope, right, on this side, right? It's attached to this pin, right, and this hook, it grabs. They say it needs to lift the load, so the load would be on this hook, right? A load that is 15,000 kilograms in mass, right? So what will tend to happen when this load is being lifted, right? The tension on the rope will be pulling in that direction. So you have a force, right, pulling in that direction. Right, now as far as the pin, right, the pin will experience some shearing, right, on this part of the pin as well as this part of the pin. Right, so as the rope pulls the object upward, right, the pin will experience shearing on this part of the pin as well as this part. Right, so that is to say that now, because we assume that this remains static, as in this will not succumb to the shearing that the pin is being subjected to, right? Essentially, it means that the forces going in this direction, the forces going in this direction will be equal to the forces going in the opposite direction. Hence, we get static equilibrium, right? But it is important to note the kind of forces that are pulling in the opposite direction, and those forces are the shearing forces, right, on this part of the pin as well as this part of the pin. Right, so you have a shearing force there, you also have an equal shearing force there. Right, so bearing that in mind, and that also this remains in static equilibrium, it means that the forces going in this direction will be equal to the forces going in the opposite direction. Right, so putting that mathematically, that means the tension on the rope will be equal to the shearing forces that we get in the opposite direction. We get two of them, so you get Fs plus Fs. So essentially, this is equal to 2Fs. Are we together here?
Yes, sir.
Right. So always bear in mind, what is this? That the whole system will be in static equilibrium. Right. But it is important to note the forces that are at play in this system. So you get this tension on the rope, right? And then because you're looking at the pin, right, you are going to get those two shearing forces, right, on both sides of the pin, right, where the hook is hooked essentially. All right. Now, bearing that in mind, they want us to calculate the diameter of the pin. Right. So now we say that if the pin, right, if the pin were to be cut, right, the pin will essentially be cut along its cross section. Right. So meaning that here the area of the cut is equal to
Secure.
the cross sectional area. It just so happens in this case that the area of cut is essentially the pin's cross sectional area, or is equal to the pin's cross sectional area, right? Because the cut would be along the pin's cross sectional area, right? Now, let us look at how we can use what we've been given. For instance, this force, right? This force here, right? So seeing that this is in static equilibrium, it means the tension on the rope will essentially be equal to the weight of the load being lifted. Right, so meaning to get that force, we can simply say that that force is equal to the mass of the load times G. Right, the mass is 15,000. Remember that the G for engineering science is 9,8, not 9,81. Excuse me. Right, and what do you get here? What is this equal to?
147,000.
147,000 newtons. Right, so if the weight of the load being lifted is equal to 147,000 newtons, it means the tension on the rope is the same. Why? Because of static equilibrium. Right? So we have that force, right? But what are we looking for? We're looking for the diameter of the pin. right? And seeing that we are looking at just the pin, we are going to be using this shearing stress. Remember what shearing stress is equal to. The shear stress, is equal to shear force divided by the area of cut. All right. Now, what is this equal to? All right, the shear force. All right. From this here, if you solve for shear force, you simply have to divide both sides by 2, meaning that the shearing force is actually half the force on the, or the tension on the rope. Right, now we've already calculated the tension on the rope, so you can simply substitute or replace this shearing force with half the tension on the rope. Right, so essentially this is equal to force over 2 times the area of cut. Now the area of cut, as we've established, that the area of cut is actually equal to the cross-sectional area of the pin. Right, the pin is circular, so that will be pi over 4 times d squared. So meaning that this will be times 4, and here you will have pi d squared.
Can you repeat that again, sir, before you go far?
All right.
Part of the force.
Right. Remember, we established that this is in static equilibrium. And if you look at the forces from the perspective of the pin, you get 2 shearing forces on this side of the pin as well as this side of the pin. And as far as static equilibrium, this force, or the forces going in that direction, are equal to the ones going in that direction. Hence, this is where that came from. That this force, the tension on the rope, is equal to 2 times essentially the shearing forces. Right. So to get the pin, or the area of the diameter of the pin, right, seeing that we are using the shearing stress, we know that shearing stress is equal to shearing force over the area of cut. Right. And then this here, right, the shearing force, if you right, taking this into account, right, we know that F is equal to 2 times the shearing force. And then solving for the shearing force, it means the shearing force will be equal to half the tension on the rope. Are we together?
Yes, sir, we are.
Right. So because we don't necessarily have this, the shearing force, but we do know that the shearing force is equal to half the tension on the rope, you can simply replace the shearing force with what it is equivalent to, which is half the tension on the rope. Do you see, Raj?
Uh, yes, I think that's what I wanted to understand about this question.
Sorry?
I'm saying that's what I wanted to understand about this question, how we are processing.
Oh, but what I'm asking is, do you get it now?
Yes, I do.
All right. So in replacing the shearing force with what it is equal to, right? So here you would have half this force divided by pi over 4, which is the area of cut, which is equivalent to the cross-sectional area of the pin times the diameter of the pin squared. Right? Now this mathematically comes down to force times 4 divided by 2 times pi times d squared. Right? Which of course is equal to force times 2 divided by pi times d squared. Right? 4 over 2 is equal to 2, which is where this comes from.
Yes.
Right? You have the shearing stress, right? We have this force, it is equal to that, we just calculated. So all we need to do here is make d squared the subjects of the formula, right? Making d squared the subjects of the formula, you will have d squared is equal to force times 2 divided by the shearing stress times pi. How would you get it?
Yes, sir.
Right, so this is equal to, the force is 147,000 times 2 divided by the shearing stress, which is 45 megapascals. Convert that to pascals. Yes,
You said we're using the force or half the force?
half the force. Remember, it's not that we're using half the force. We are guided by this here.
Okay.
Right? We are guided by static equilibrium conditions that states that the sum of forces in one direction or along the same set of axes is equal to 0. Meaning, in this case, forces going up are equal to forces going down.
No, so I don't think you understand his question. What he means is that he didn't see that you already included the half in the formula. That's why he's asking if you're using the force or half the force, because he expected you to write half and force. Not
But we
putting it
did write
right
the
like
half.
that. Yeah, I think he doesn't understand that part.
Oh,
Yeah, now
does
I
it get it?
see that the half was included.
Yeah,
Yeah. Thank you.
yeah.
Okay. All right. Thanks. So, and then what do you have here? Times pi. Right. And what do you get here?
Should we square it already, sir?
Now,
Should we use the
just
square root?
just calculate this exactly as it is. So whatever you get here will be equal to d squared.
Oh,
So whatever you get here is equal to d squared, right? And then the answer you get, right,
square
we are
it.
going to use the square root on it.
Two hundred and 96 times 10 to the power 6
200
minus 6. 207, 96, 2 times 10 to the power minus 6.
times 10 to the power.
Minus 6.
So you said 2,
207,
207.
96,
207,
comma,
comma,
962
962
times 10 to the power minus 6.
minus 6. Are we all getting the same thing here?
Yes, sir.
All right. 207, comma 962 times 10 to the negative 6. Right. So that is what d squared is equal to. But we are looking for d. So to get d now, you simply say d is equal to the square root of what we just got. So 207, comma 962 times 10 to a negative 6. So what is the
I
square root
said
of
there
this?
14.
it's two. So on the d squared is 2079,625 times 10 to the power minus 6. That's what I'm getting.
So the comma is after the 7.
It's after the 9.
No, it's fine like
It's after
that,
the
sir.
9. Okay. Let me
No,
do it
not
myself.
true. Okay.
So it's 147,000 times 2 divided by 45 times 10 to the 6 times pi.
Yes.
Right. So I am getting the same as the last speaker.
Yes.
So in the exam, just be careful of how you punch your calculators. That will either make or break you. Because unfortunately, the only way we can tell that you understand the content is by getting or is by writing the correct solution. Unfortunately. So if you make a mistake, obviously marks will be docked for that. So yes, this was supposed to be 2079, comma that. So meaning here we have 2079, comma 625 times 10 to the negative 6. Right, now if you now apply the square root, what do you get?
45,602 times 10 to the power negative 3.
45,603.
Yeah.
10 to a negative 3 meters.
Yes.
Remember, this is the diameter, so it has to be in meters.
So, but by that first one where you worked out 2079,625 times 10 to the power of negative 6, I also get 207.962 times 10 to the power of negative 6.
Just say that again.
So, where you have your answer as 2079,625 times 10 to the power of negative 6, I also get like, Faika got 207.962 times 10 to the power of negative 6.
Okay, just check.
I literally double checked like twice or thrice. I get the same answer she got.
So I actually now punch it in again. Then I got what you got also now, 3,779.
Yeah, you must check yours. Either you have 2 zeros instead of 3 here, or you have 5 zeros instead of 6 here. One of the two.
That's why I was saying we must. That's why I was
Oh,
asking
I
if you should
see,
square it
sir.
from there, sir.
I
You
see
see
the
that?
mistake we made. I had 2 zeros by the 14,700. It's supposed to be 3
Right.
zeros,
Yeah,
and then I got what you
yeah,
got.
yes. Someone was saying something else there. I didn't
No,
quite get.
no, I was just saying that's why I feel like it's much safer if you square it from there, because if you write that answer, that is squared, and you have to square it again,
Yeah.
you make a mistake.
As far as mathematically, you can do this anyhow. I actually prefer using the square root here as well, right? But this was to try and break down how we get to this here,
Okay,
right?
sir.
Otherwise, you could have done this here. I prefer doing that, right? As
That's
I'm
why I
saying,
do it this way.
mathematically, your approach doesn't really matter. Even this here, if you feel like this is right, this is too much, right, of like breaking down or simplifying the formula, you can simply use it like this here. It's fine. Right, I'm able to get to this point in my head, right? This was just a breakdown of how to get here,
Yes, sir. Because sometimes
right?
you can
It is much simpler to use the formula in its simple form, well, for me anyway.
yes, sir. Because sometimes
Otherwise, mathematically,
when we
yes,
try to do what you do, sometimes we can make mistakes. So I think it's better for us to substitute from the get go.
from the get-go, that is fine.
Yeah,
Absolutely fine.
yeah,
As I'm saying, mathematically, it doesn't matter much what you do. Once this is established, right, however your approach is mathematically, doesn't
yeah.
matter, right? As long as you understand that if your answers are this small, right, always make use of engineering notation, right, for accuracy purposes.
Okay, sir.
Yeah. Any more questions? Right.
Yes, sir. I want to ask you
So
something.
Okay.
Oh, sorry, the lady can go first.
April, go.
So yeah, in the textbook by the summative assessments, there's some questions that say we have to draw the stress strain graph. Well, that's possibly in the exam.
Yes, it is possible.
Can you maybe
Um,
do an example on that?
yeah, we will. I just have to find a suitable one. I actually forgot about that. That is quite possible. I'll find a suitable one. Uh, Perhaps I can do a video on it and upload it on my channel as well.
Okay. Uh,
Okay, so
okay.
Right?
Sir.
Because for now, I just want to address the questions. I have another session I need to prepare for at 12.
Okay, sir. Can I ask you in 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 this kind of in the similarity in this type of question. So sometimes they can give you like
Mhm.
a hook. They can give you like a hook like that, and maybe it has I don't know how I can put this.
But just send it in the group and ask your question
Okay,
there.
all right.
Do
I
you
will
do you
send
do you remember what
send
they were?
a structure. Let's say a hook has that pin that end pin.
Uh-huh.
Then the hook is it hooked on that pin. So it's basically the same approach as this one. The
Yeah.
force is this.
If
So it's always
the
static.
approach. Um. Let me see. Let me see. Uh, okay. Okay. To answer your question, where's this thing? Where's this thing? Where's this thing? Uh, I think I've seen that kind of problem, or I think I know what you mean, but I'll
Yes.
make an example of this problem. I'm just not sure if it was 2020. I think it was 2023. Let me check quickly. Right, but the point here is any and all problems based on hooks and pins, the approach will always be the same.
Okay.
Let's just look at, oh yeah, see like this one. So this one
Yes.
is different, but it's still a hook and you still have a pin. Right, the approach will be the same.
Okay.
Right, the approach will be
So
the
that
same.
means in
Yeah.
both sides we have FS.
In both sides, you have let me just take a picture of this quickly. Uh, right, as much as the hook is different from the one we just looked at, right, the
Yes.
principle used is the same. Right, so you're going
Okay.
to have, so on this side, perhaps on this one, the hook will be, say, will be
On the
there
bottom. Yeah. Yeah.
at the bottom, and the, the,
Yeah.
the, the weight of the load will be pointing, obviously, right, in that direction,
Yes, sir.
right? Meaning that as far as the tension, you'll have a force there, and then because the problem is based on the pin, we look at the forces that the pin is being subjected to, and those forces would be right here and right there.
Yes,
So you
sir.
have Fs here, you have Fs there.
Yes.
Essentially, the approach is the same. Do you see
Okay.
that?
Okay. So
Yeah.
those the arrows for FS they are going up if the pin is down. If the pin is pulling down.
The shearing
Let's say
forces will
let's say we have
will
a hook
always go
there.
against. Sorry.
Let's say we have a hook on the pin is pulling down. That means the
Yes.
FS they're gonna go up.
No. The pins always go against the, what is this, the tension or the force on the rope, or the tension on the rope.
Okay. Yes, sir. All right.
Right, because remember this is being pulled, so this is going in that direction, so the shearing would be in that direction.
It's being pulled in in which direction, sir?
It is being pulled in this direction. It is being pulled up.
Okay. Okay.
You see that?
Yes, I do.
Right. So the point here, though, is that the approach is the same.
All right.
You look at it. You look at the fact that this will be in static equilibrium, right? And you use conditions of equilibrium, right?
Okay. All right.
Right. Um, April. What did you say? Oh, the graph.
The graph, so
Right. Yeah. I'll look for a suitable problem. Excuse me. I'll look for a suitable problem for drawing the graph. Ooh. Yeah, I totally forgot because I think you also have to. They sometimes ask you to like grade to get the gradients, right? So I look for a suitable problem, one that includes where you have to calculate, say, the gradients and show you how to approach those ones, right? But
Okay.
that one I would have to do on my own and then upload on my channel and then send you the link.
Okay, sir.
okay, so
And then if you have questions, we can look at questions together.
Okay, sir.
okay, so
I don't know when you'll have time, say, to do that video. You said tomorrow morning around this time you have another class, right?
One other class, yes.
I think that one is based on heat.
Heat, yeah.
Okay.
So it will
So
be based on.
maybe I'm just assuming maybe tonight you can maybe record that video and send it to us. So tomorrow when we have the class of heat before we continue with heat, then maybe you can ask you some questions.
100%.
Okay.
100%.
Like it,
So, and then
time is
also,
time is short.
Okay, before you continue, let me just stop the recording because we are no longer doing any problems. And then we can just talk.